Welcome to this third and last introductory lecture on proofs. In this lecture, we will introduce a single new proof technique called proof by cases. We'll show a few examples of it and illustrate a couple variations of it. In this first segment, we will start by an example. Namely, we will try to prove the following theorem. For every integer n, the number n squared plus n is even. So let's start writing a proof right away. That doesn't sound like a very difficult theorem to prove. It's a universally quantified theorem. So as usual, we're going to let n denote an arbitrary integer. And so now the question is, how do we infer that n squared plus n is even? Well, it turns out it's a little bit hard to do because we don't have much information to start with other than n is an integer. So this is actually a situation where we would benefit from having more information. For example, if we knew that n is odd, then maybe it would be easier to prove that n squared plus n is even. But we don't know this information. However, the crux here is to realize that any integer n must be either odd or even. There are only two cases, and these two cases cover all the possibilities for n. And this is where the proof by cases becomes very useful. So here is the rest of the proof. Since we know, this is an axiom, we don't have to prove it here, that n must be either even or odd, we can prove this theorem by completing two subproofs corresponding to two cases. The first case is when the number n is even. So there will be a proof of this proposition here when n is even. That will be case 1. So we don't forget the case number 2. Let's write it down right away. Case 2 is when n is odd. We will also have to prove this proposition for the second case. But since, as we argued here, one of those two cases must always hold. In other words, we cover every possible element of the universe by covering the even integers and the odd integers. At the end, if we could prove this proposition in both cases, then we've proved it for every integer. So now let's go back to the proof and complete the proof of case 1. So now in case 1, we assume that n is even. In other words, what we're trying to prove now is that if n is even, then n squared plus n is even. Notice we switched the theorem, which was just a simple proposition, into a conditional. How could we do that? Well, we just assume that n is even, and that gives us more information to infer the conclusion, hopefully. So let's see if this works. So if n is even, then there must exist an integer k such that n is written as 2 times k. That's the definition of being even. So now we could start from n being 2 times k and compute the value of the expression n squared plus n, since we're trying to prove that it's even. So n squared plus n is equal to what, given that n is equal to 2k? Well, it's equal to 2k squared plus 2k. In other words, 4k squared plus 2k. Hey, we're trying to prove that this expression ends up being even. So we should try to write it in the form of 2 times some integer. So let's factor out a 2 here from each term to get 2 times 2k squared plus k. But that last expression here, 2k squared plus k, must be an integer, since k is an integer. So in conclusion, n squared plus n is equal to 2 times k prime for some integer k prime, namely this one. But since n squared plus n is equal to 2 times an integer, by definition, it's even. And that is exactly what we needed to prove for this theorem. Now, of course, we're not done with our proof. We're only done with the subproof for the case n is even. So we only taken care of half of the domain for n. So let's start the proof for case 2 where n is odd. Remember, what you are trying to prove in this second case is that if n is odd, then n squared plus n is even, which is our top level theorem here. So let's go ahead and assume that n is odd. Therefore, there exists an integer case such that n is equal to 2k plus 1. And again, we're going to now rewrite the expression or the term n squared plus n and try to prove that it must be even in this case as well. So n squared plus n is equal to what? Well, it's 2k plus 1 squared, that's n, plus 2k plus 1, that's another n. Let's multiply out and rearrange to get 4k squared plus 6k plus 2. And we're still trying to prove that that expression is even, remember. So let's try to factor out a 2 out of each term, and we get 2 times 2k squared plus 3k plus 1. We know this term is an integer. It must be because k is itself an integer. Therefore, we were able to write n squared plus n in the form 2 times some integer k prime. And that is the definition of an even number. So we can conclude that n squared plus n is even. And this is the conclusion of the second subproof, in other words, the proof of case 2. Now, we're still not quite done with the proof of the original theorem. What we proved is that the quantity n squared plus n is even in case 1 and also in case 2. So the conclusion we can draw from that is that n squared plus n is even in all cases. And by all cases, I mean, remember, it must be the case that case 1 and case 2 together cover all possibilities, cover the whole domain for n, which of course is true here. So only then can we infer that for any arbitrary n, n squared plus n is even, because we've covered all possible cases for n. It's either odd or even. Now remember, n is just an arbitrary integer at this point, so we always conclude our proof of this universally quantified theorem by applying the universal generalization rule to infer that indeed for every integer n, n squared plus n is even. And that concludes our proof by cases of this theorem.